We've got our FD-RX7 project car here at Highlands Motorsport Park today, and we're going to put it through its paces and essentially finish off the tune. Now, if you haven't followed the rest of our FD-RX7 episodes, just to bring you up to speed, the car is essentially a low kilometre stock 13B, and it's running a Turbolon turbo kit which consists of a stainless investment cast exhaust manifold running twin TurboSmart external wastegates and a BorgWarner EFR 8474 turbocharger. The fuel system upgrade as well, front mount intercooler in a V-mount configuration from Vinifab and a few other bits and pieces. It's all controlled with an Adaptronic modular ECU. And we finished off on the dyno, and wherever possible, I like to always take the cars off the dyno and just confirm out in the real world that the numbers that we're seeing in terms of air-fuel ratio, boost pressure, etc. knock, maybe not essentially for a rotary, because if the engine knocks you're going to very quickly know about it, but essentially making sure that everything we saw in the dyno stacks up under real world conditions. And this is something that a lot of tuners don't do, but I personally find it essential. A reason for this is what we find is on the dyno, despite a quality dyno, and even if we've got a really well designed dyno cell, it's very difficult to accurately replicate the airflow and hence the temperatures that we're going to see in the engine bay at speed on the road. And we don't really race our cars on dynos, so what we really care about is what the performance is and what the tune's like out in the real world conditions. So that's what we're going to do here. And essentially, we're going to just make sure that everything we saw stacks up, everything's the same as what we saw on the dyno, and I usually expect to have to make a few minor changes. Hopefully they shouldn't be too major, but it's always a good idea just to check it out and make sure. So let's jump in the car, head out on the track, and we'll see how I go through this process. All right, so the first thing we want to do before we start looking at our data and deciding how good or bad our tune may be is we want to spend some time and get rid of any heat soak from the engine. And this can really affect our results, particularly if some of your compensations aren't quite on point. So particularly if you've had the car idling for a while, it's always a good idea to just let all of those temperatures stabilize and come back down to normal operating temperatures. So here I'm predominantly looking at my engine coolant temperature and my inlet air temperature. This might take maybe half a lap, a couple of minutes of driving just to get everything back down to a normal temperature. Once we've done this, we want to actually understand what we're going to try and do here. And really, we're going to be driving the car in a couple of different ways, replicating what we saw on the dyno. So what we want to focus on, particularly for a street car, is the drivability areas of that map. We want to focus on the areas between, let's say, about 2,000 and 3,500 RPM part throttle, the areas that we're going to be using a lot, particularly under cruise conditions. So we want to gather a lot of data there and basically look at how close our mixtures are to our target. And again, we're likely to see some small variations. The other piece of data we're going to collect is we're going to do a full throttle or a few full throttle ramp runs or acceleration runs. We're not on a dyno, so it's not really a ramp run, but this just replicates the way we drive the car on the dyno. And this is simple. We just need to choose a gear where we're going to be applying a reasonable amount of load to the engine. We also want to make sure that it's a gear where we're not going to end up traction limited. Third or maybe fourth gear is a good way to go, particularly with a turbocharged rotary like this. We do need to be mindful, obviously, of speed limits. Now, we're here at a racetrack, so we've got the benefit of no speed limits, no pedestrians, and we know there's not going to be any oncoming cars, so it's the perfect conditions. And of course, not everyone's going to be lucky enough to have access to a racetrack to use like we are here, but this still can be done on the road, but there's a few caveats around it. It really comes down to a little bit of common sense. Obviously, if you value your driver's license, watching out for your speed just makes sense. We don't want to be exceeding the speed limit. The other thing we want to do is always concentrate on driving the car. We want to focus on the road and what's going on around us. We don't want to be spending time staring into a laptop screen. So this is where using a helper can be a real advantage. You can have the helper concentrate on using the laptop, and that gives us the ability to just focus our efforts on driving the car, or do it around the other way. So what are we doing here? How are we going to gather that data? Well, rather than trying to focus on what's going on inside the laptop, and this is really good as well if you are doing this tuning on your own, what we're going to do is gather some data using the Adaptronic logger. And we're now at a point where all of our temperatures are stable, so I'm just going to start recording my log file here. Press save, that'll start recording a log file, and now I'm just going to drive the car. So for this first part of my session here, I'm just going to be concentrating on that area I talked about, the part throttle area. I want to vary both my throttle position as well as my RPM. Now this can be a little bit tricky. What we want to do here is get to as many cells in the fuel table as we realistically can. But of course, out on the road where we don't have the benefit of a load-bearing dyno, every time we add a little bit more throttle, the car is simply going to accelerate and the engine RPM is going to increase. So here we can use a technique called left foot braking. And this just, as its name implies, is us using our left foot on the brake pedal to apply a little bit of load through the brake system. And by doing this gently, like I'm doing now, we can increase the throttle opening and get to higher low points in the fuel table without the engine accelerating. Now it does take a little while to build up finesse doing this. The other thing we need to be mindful of is that we're obviously going to be putting heat into the braking system, so this needs to be managed. So again, a little bit of common sense applies here. We're going to use short periods of left foot braking followed by longer periods completely off the brakes, just allowing those brakes to come back down to normal operating temperature. So here the other thing we need to understand is the way that we're going to drive the car. Now we want to be nice and smooth when we're driving the car. The reason for this is if we apply large throttle inputs or we're erratic on the throttle, we're going to affect our results with transient acceleration enrichment events or enleanment events, and this can really mask the true air-fuel ratio. So nice smooth input. So you'll notice that while I've been logging this data, I've been solely in fourth gear. Now that's not always going to be possible if you're on the road, but don't worry, we'll show you some tricks as well that you can use to filter out some of the data that's maybe a little less useful. Alright, so I'm just going to continue and drive another lap, gathering some more data so I can fill in as many of these cells as I can. And the idea here is to get some good quality data. We want to get as much data as we can covering those cells. The more hits we can get in each cell, the more reliable our data or more meaningful our data is going to be. So I'm just going to continue, do another lap or two and gather some data, and we'll go back to the pits and have a look at that data and see what it tells us. We've got our data, we're back in the pits here and we're having a look at it. This is the built-in log viewer that the Adaptronic Eugene software comes with. Frankly, looking at this, it's a little hard to really know what to make of it. The data here does include our target lambda and our air-fuel ratio. So these are two of the key aspects we need to monitor, but it's really hard to do anything useful with the data in this format. So what I prefer to do with the Adaptronic software is actually export the log file as a .csv, which means that we can then view it in a range of other products. In this case, I'm going to be using Mega Log Viewer HD. Let's head into that software and see what the data looks like. Alright, so now we've got the data set up in Mega Log Viewer. Again, at face value, it's hard to really take much notice of it. Our top plot here in red, we've got our RPM. And then the next plots down, we've got our inlet manifold pressure and our throttle position in yellow there. The next plot down, which is really our key one here, is our lambda and our target lambda. So really, if everything's absolutely perfect, we should see these pretty much overlaid directly on top of each other. Now we do need to be a little bit mindful again, as I mentioned, transients, we're going to see some errors there. If you're completely off throttle, probably going to also see some errors there. So we do need to be a little bit mindful of how we read this. Now, what we can see is that for the most part, it looks like the plots are pretty close, but we've got some areas where there's definitely some work to be done, and this is exactly why we do what we're doing here. Ideally, if we've got everything right, we should see our lines within about 2% of each other. If I just click on that particular point there, you can see that that's pretty much exactly the case. Our lambda target there, lambda 1, or 14.7 to 1 if you prefer air-fuel ratio units. We're at 0.976, let's round that to 0.98. So we are within 2%. So it actually looks worse than it really is in reality. But again, very hard to make specific changes, and one data point out on its own, it's a little bit hard to really draw too many conclusions from that. That's why I wanted to gather a lot of data, and what we're going to do is come over to the histogram and table generator tab in Mega Log Viewer HD. We'll click on this, Now everything becomes a little bit more useful. So a histogram basically allows us to set up some bins, and it will log data into those bins. So what we've done here is we've got the table set up, essentially exactly the same breakpoints as our fuel table or VE table in the Adaptronic. We've got inlet manifold pressure on the vertical axis, we've got RPM on the horizontal axis. Just to make things a little bit trickier here, the axis directions are different. So here, as we go from the bottom to the top, our manifold pressure is increasing. If we switch over to our Eugene software, we can see it goes the other way. So we just need to be mindful of that. But once we've got our head around that, we can see that the breakpoint's essentially identical. Right, let's head back into the software and we'll see what else we've got going on here. So the parameter that we've actually got being displayed here is a custom math channel that I've created, and I've called this math channel, we can see it here, Adaptronic Lambda Error. And all it's really doing is taking the measured air fuel ratio, comparing that to our target, and giving us an error as to how far away we are, representing that as a percentage. Now the way I've represented this here, negative numbers, which is what we've got for the most part in this table, this means that we are richer than our target. The good thing about this is the more data we gather, the more hits we get in these cells, the more we can trust the data. And over here, we can see exactly how many records we've got. Almost 6,000 hits in that table. And the color coding here weights the values based on how many hits we got. So bright green, or the dark green I should really say here in the middle, this is where we've got the most hits. This is where we spent the most of our time. We've got some lighter green and some yellow here. These are some outliers where we haven't quite got as many hits. We can sit in a particular cell and it will show us here we hit that cell 147 times. If we go into the middle here, we've got 1900 hits in that cell, so we can be pretty sure that that's going to be an accurate representation of our error. Out here on the right hand side, didn't really get up to 4000 RPM that much, I wasn't trying, only 21 hits. So that allows us to decide how much notice we want to take of that data, and we can see for the most part the areas that we really were hitting a lot, we are within about 1 to 2%, so already we're actually pretty good. And we need to be realistic about what we can expect with our tuning. You are never going to have your air fuel ratio perfectly always track your target. That's what closed loop controls for, and even OEs rely on this. So if I'm within 1 or maybe 2% of my target, I'm going to be pretty happy with my work. That being said, we can apply what we've learned from this table into our VE table to improve things a little bit more. This becomes an iterative process, so it might take 1 or 2 goes. We'll go back out, gather some more data and repeat this process until we're getting as close to zero error as we can. Now, there are some other little tricks that Megalog Viewer allows us to do. You remember I've talked a little bit now about how important it is to be smooth on our throttle inputs, and we don't want transient enrichment ruining things for us. So out here on the right hand side, we actually have a range of filters that we can apply. We can make our own custom filters, but here we've got filters for air fuel ratio out of range, if the engine coolant temperature is cold, if we're idling, if there's a sudden change in RPM, if the throttle is closed. That's a really good one to eliminate garbage data when we're in deceleration, fuel cutoff, and transients. Now, I'm not using any of those at the moment, and I can't get too deep into this, otherwise we'd be here for another hour. It's just good to know that those filter options are available there, and it can really allow you to dig in deep on some good quality data, because this becomes a case of garbage in, garbage out. So anyway, that's how we gather our data. Really important to understand that, because as you can see, we didn't need to be glued to a laptop screen. In fact, we can completely ignore it. All we're doing is gathering that data out there, coming back into the pits and the safety with the car stopped. We can analyze that data and make our changes. That's all well and good. We've only really looked at our cruise situation there. We obviously also want to see how good our tuning is with a wide open throttle ramp run. So we're going to head back out on the track and we're going to replicate that. What I'm going to look for here is a long piece of track where I can really load the car up. So let's get back out and get us up and running again. All right, we're back out on track, and the same process as last time. We want to start by making sure that we've got rid of any heat soak. Our engine and air temperatures are at normal operating temperatures. And what we want to do is choose a long section of straight road where we know we can load the engine up and we don't have any problems with running out of road. Also want to use a high enough gear that we're putting the engine under some reasonable load. First and second gear probably not that smart. So here I'm going to use third gear. We're just coming up to a long section of straight and we'll get ourselves down to around about 2000 RPM and really trying here just to replicate the same sort of conditions we used for the dyno ramp runs. And we're going to get onto this straight and it's going to go smoothly through to full throttle and accelerate all the way through to the rev limiter. Alright, so acceleration run complete there. Now we've logged all of that, so we can go back to the pits and have a look at that. Again, we don't need to be trying to analyze anything on the laptop while we're actually doing our ramp run. And that's important because we can concentrate all of our energy on keeping the car in a straight line, making sure we're in control. At the same time, I do like, wherever possible, to have a wideband air fuel ratio meter mounted on my windscreen, and you can just glance at this out of your peripheral vision. If you've got a boost gauge, that's also great too. You can just monitor those gauges out of your peripheral vision. If you see anything you don't like, you can import the run, have a look at your data back in the pits and decide what changes need to be made. It's all about creeping up on the optimal tune in a safe way. We don't want to stay in the throttle if our air fuel ratio isn't where we want it to be, or the boosters may be spiking above what we expect. Alright, let's head back into the pits and we'll have a look at that data and see what that can tell us. Alright, so we've got our data log downloaded here, and what I've done is just narrowed in or zeroed in on that acceleration event there, our wide open throttle acceleration, just so we can focus on that. And again, we've got the same channels. We've got our RPM up the top, the yellow trace in the middle is our throttle position, the green is our manifold pressure, and then down below here we've got our target air fuel ratio, or lambda, and our measured lambda. So first of all, what we want to do is check what our boost was doing. And we can see our boost smoothly comes up to around about 190 kPa, peaks here at just under 200 kPa, or 1 bar of positive boost. So all pretty good. It's doing pretty much exactly what we saw on the dyno, so nothing wrong with that. Looking at our lambda though, we can see first of all we've got a bit of a lean spot here as we tip into the throttle. So this isn't really necessarily tune related in terms of our VE table though, so I wouldn't be trying to correct this in the VE table. This is as we've tipped into the throttle, so this simply is a need for more acceleration or transient enrichment. So we're going to ignore that and focus really on what happens once we get up to our wide open throttle ramp run and we are starting to accelerate. So we see as we first of all ramp onto boost, we're following our target pretty accurately. I'm quite happy with what it's looking like there. Got a tiny little lean spot here, but we're within about 1 or 2% right through that area. What we can see, and it's not necessarily a problem, is in the area where we are at full boost, we are a little bit richer than our target. We're in this case 0.74 and a 0.77 target. As we get up to higher RPM here, up at about 6,800 RPM in this case, we're getting a little bit closer, 0.76 on a 0.77 target. Again, around about 1% error I'm okay with, and generally I'd prefer to err on the side of being a little safe, a little rich I should say, which is safe, rather than a little lean. So nothing strictly wrong. This is actually a pretty good starting point, but yeah, I would probably want to pull a little bit of this richness out here between, in this case, around about 4,200 RPM and probably around about 6,500 RPM. Now, using the information in this data log, we've got everything we need. We've got the RPM points here from our RPM trace, and we've got our manifold pressure, or IMAP, which is the other axis for our main VE table. So we can be pretty pinpoint accurate in making these changes. Again, it's an iterative process. We might not get it perfect on our first try, but normally with 1 or 2 adjustments to this at the most, we'll have our fueling dialed in perfectly out on the track. And at this point, we can be pretty confident that our fueling is accurate under our normal operating conditions, our cruise areas, our transient areas, and then of course our wide open throttle areas. So this is how we can use some of the technology available to us in terms of the data logging to
really speed up our tuning as well as making it a lot more accurate and safer for us when we are driving the car out on the road. What we've just looked at today is the last step of the HPA 10-step tuning process. The other 9 steps were completed previously on the dyno, and in our previous episode we looked at some of the aspects of that. Now, if you do want to learn more about the tuning process, if you want to learn how to tune from start to finish, then our practical standalone tuning course is going to be perfect for you. That practical standalone tuning course is a generic course. It's not designed solely for tuning rotaries. It's not designed solely for using the Adaptronic software. It just happens that we're in the middle of filming a worked example for that course at the moment. So that's why we're in our FDRX7 with the Adaptronic. How the course works is it teaches you the principles behind the operation of the engine and the ECU. You'll then learn the process of tuning, and what we've done, as I mentioned there, is broken the entire tuning process down into the HPA 10-step process. The reason we've done this is because for novices particularly, when faced with a freshly installed ECU with no base map, we know it can be a little bit daunting knowing where to get started. So with that 10-step process, each of those steps is relatively quick and easy to complete, and by following it from start to finish in no time, you've got to the end like we have right now. You've got a completely tuned engine that's delivering great power, great torque, and most importantly, great engine reliability. Following that process from start to finish will also ensure that you don't overlook any critical areas that could waste time, waste money, or even potentially damage your expensive engine. Following that 10-step process, which is generic, applicable to any aftermarket standalone ECU and any engine, we then move into our library of worked examples, which is what we're filming for now. And in that library, we choose a different engine and a different ECU each time, and we dive into that 10-step process, and you can follow it through being applied in real time. If you are interested in learning more, you can click the link in the description.
If you like that video, make sure you give it a thumbs up, and if you're not already a subscriber, make sure you're subscribed. We release a new video every week. And if you like free stuff, we've got a great deal for you. Click the link in the description to claim your free spot to our next live lesson.